Hi, I'm Jason West talking to you from my home in North Carolina. Um, Many of the talks in this session are focused on the drivers and changes in emissions and air quality in Asia. We're taking a bit of a different look here in that we're looking at how the sensitivity of the atmosphere of global tropospheric ozone to changes in emissions from different regions. And we'll highlight here how we think that emissions from South Asia and especially Southeast Asia are particularly important, that the atmosphere is particularly sensitive to emissions from those regions. This is work led by Yuchang Zhang at Duke, and I'm at UNC, and I want to thank everybody else that contributed to this work. So we'll motivate this by looking here at how emissions have changed in the past. This is global anthropogenic NOx emissions in 1950. And we'll step forward by decades, so 1960, 70, and you see by 1980 that emissions have kept basically the same spatial distribution, though emissions have increased quite a lot. The spatial distribution is the same, dominated by emissions from Europe and North America. That started to change after 1980, so 1990, 2000, 2010, with emissions decreasing from North America and Europe, while they're increasing here in especially Asia and especially China. So while over this period, 1980 to 2010, global anthropogenic NOx emissions increased by 21%, and they also shifted southward. And we see the same southward shift for increases that have happened over the same period in anthropogenic carbon monoxide and non-methane VOCs. This was interesting to us because we knew that these are results of model simulations for a study that I led a long time ago now, that the global tropospheric ozone burden is more sensitive to emissions from the tropics in the southern hemisphere, or we could say subtropics as well. Here, this is the change in ozone burden per unit change in emissions from Southeast Asia, from South Asia, from Australia. These are much greater sensitivities than we saw for mid-latitude regions. And this greater sensitivity to emissions from tropical and subtropical regions is due to strong photochemistry, so a lot of sunlight, high NOx sensitivity where we have more remote regions, and especially the southern hemisphere and areas along the equator. And one thing we think is particularly important is the strong convection. So pollutants are lifted from the surface up to the middle and upper troposphere where they live longer and produce more ozone. And this is the case in tropical and subtropical regions, despite the shorter ozone lifetime there. So there's more Hox radicals that destroy ozone because of the more greater water vapor there. And despite that, we see this greater sensitivity. Well, we looked at this in a paper led by Yuchang. This was 2016, where we looked at the change in tropospheric ozone burden from 1980 to 2010. And here we ask the question, what are the effects of changes over this period on global tropospheric ozone due to changes in the global spatial distribution of short-lived anthropogenic emissions, holding the magnitude of emissions constant. Secondly, the changes in the magnitude of the emissions holding that spatial distribution or the equatorward redistribution constant. And the third factor was the global methane change. And these were our results from that paper. And we were surprised to see that the spatial distribution change was as important as it was. So methane here and the magnitude change are shown, but the spatial distribution change is over half of this total change. Not only that, but it has the best ability to explain this in the modeled spatial pattern of the tropospheric ozone burden change being greatest over here South Asia. So this was suggesting to us that perhaps emissions from South and Southeast Asia might be particularly important for global tropospheric ozone, but we didn't investigate that further, and that's our goal here. So our objectives today are to analyze the contributions of changes in anthropogenic emissions from 10 world regions to the global ozone burden, again, focusing on 1980 to 2010. And it's our hypothesis that emissions increases in tropical and subtropical regions were particularly important for this overall change. The methods that we use, we're using CamChem, which is the standalone atmospheric chemistry version of CESM. One important point is that we're using global meteorology that's fixed. So we run 5-year simulations. The first year is spin up, so we're presenting results as a 4-year average. That means that we're focusing on the effects of emissions changes, ignoring any possible changes of climate change or climate variability. These were the simulations we used for our previous study, simulating 2010, 1980, and a control simulation where we singled out the effect of methane. Now we're adding 10 new simulations looking region by region. Those 10 regions are up here. And one by one, we return those regional emissions to 1980 levels. And then by difference with the 2010 simulation, we single out the effect of each region's change in emissions. Okay. These are our results. So this shows the, on the left here, the global tropospheric ozone burden change. The greatest effect is the methane increase, but you see pretty big effects from several different world regions. And some decreases where emission reductions taking place between 1980 to 2010 caused the global ozone burden to go down. So emission reductions from North America, Europe, and the former Soviet Union. You can see that here in these emissions plots of the changes in emissions from these different regions. One of the things I'd like to focus on here, the global burden change was increased 28 teragrams. If we add up South Asia, East Asia, and Southeast Asia, that's 15 teragrams. So over half of the total comes from these 3 regions. So a pretty pronounced effect from these 3 regions. If we look in particular, here's Southeast Asia, which has as big of an effect as East Asia. But looking at the emissions from Southeast Asia are much smaller. The emission change are much smaller than from East Asia. And actually, that's the case for South Asia as well, where its emissions changes are smaller than East Asia, but the effect on tropospheric ozone is comparable. You can make a similar argument for Central and South America and for Africa. This looks at that effect spatially. The effect of the methane change is pretty smooth spatially. North America and Europe here cause emissions are going down and causing tropospheric ozone to go down. And where that tropospheric ozone change happens is mid-latitudes toward the Arctic. East Asia as well has a big effect in the mid-latitudes toward the Arctic, with some effects here extending toward the equator. But the big things that we want to emphasize here are Southeast Asia and South Asia, which have big effects through the tropics and subtropics. When we go to the next slide here, these are zonal plots, so from latitude southern hemisphere to northern hemisphere and through the depth of the atmosphere. North America and Europe here have big effects, but they're contained here, and they don't reach a very high elevation in the troposphere for the most part, whereas East Asia now has some effects toward the equator and some of its emissions reach higher in the atmosphere, but most of it is contained in the mid-latitudes toward the Arctic. In Southeast Asia and South Asia here, then we have this lofting of air up to the middle and upper troposphere where it lives longer, and that explains in part the greater sensitivity that we see. One of the things we did here was to compare this with the HTAP2 simulations. You might remember that HTAP2 analyzed 20% emission reductions of all anthropogenic emissions. We've taken the ozone burden change and normalized that by NOx, though really other emissions were changing as well. Showing the simulations for 6 regions, there's some variability, greatest in South Asia. If we look at this global effect, that's greater than any of these regions, suggesting that there must be some other region for which there's a greater sensitivity that HTAP2 didn't simulate. When we look at CamChem, then, again, this is not exactly the same experiment as we showed for HTAP2. These are historical 1980 to 2010 changes, again, normalized by NOx, but other emissions are changing. Now we see a really big sensitivity to Southeast Asia, Pacific, Australia, and New Zealand, and Central and South America. Among the regions that HTAP simulated, we get South Asia having the greatest sensitivity. but HTAP had missed these regions here, and we suggest that for future experiments like HTAP, they should really think about these tropical and subtropical regions. We spent a good bit of effort in our previous paper and in the new one coming out that hopefully Yu Chang will publish soon to compare against observations. So this is Jerry Zimke's satellite observations, satellite-derived ozone columns. And the time period is not exactly the same as ours, but what we really want to highlight is the spatial distribution of that change. Now for our model below, the spatial distribution of the change looks pretty similar. So that gives us increased confidence in what we're doing. We also compared with Iago's observations. So these are commercial aircraft. And this was Audrey Goodell's work. Looking here, again, the years don't coincide perfectly with ours. Looking here, the regions that have the biggest changes in the observations here, this is India, Malaysia, Northeast China and Korea, Persian Gulf, and Southeast Asia. Those are the 5 regions here that we also find the biggest effect. These are normalized by decade, so ppb per decade. And you see that actually the numbers from the Iagos measurements are bigger than ours. And that's, we think, potentially important. It could have to do with the choice of years that doesn't coincide perfectly with ours. So perhaps not much was going on between 1980 and 1994, but it could also be that perhaps we're missing something important in the model. Okay, so I'll conclude. We showed that the changes in the spatial distribution of global anthropogenic emissions are most important for global tropospheric ozone. In this period, 1980 to 2010, actually over half of the global ozone burden increase was due to emission increases from 3 regions: East Asia, Southeast Asia, and South Asia. And we showed that actually Southeast Asia shows a particularly strong sensitivity to emissions, even though the change in emissions from that region hasn't been as large as for East Asia and South Asia. When we look to the future ozone burden will be determined mainly by emissions from the tropics and subtropics. And we're concerned that a continued equatorward shift toward the equator may cause the ozone burden to increase, even if we take action to reduce global ozone precursor emissions. So that's all I have to say. Thank you for your attention. I want to thank everybody, and I look forward to your questions.